In the last lesson video, I finished with a lovely question about Hall probes. So, what I'm going to do this time is quickly recap the question and then go through the answer. So really make sure that you have attempted this first. So, recapping the question, here's a diagram of a Hall probe. The current is going left to right and the field is going bottom to top. The Hall probe is made of metal. So, consider each of these individually. What will be the effect on the magnitude of the Hall voltage and the direction, the sign of the Hall voltage, if we change the direction of the current? What will be the effect on the magnitude of the Hall voltage and the direction of the Hall voltage if we change the direction of the magnetic field? So the current is going left to right, the field is going top to bottom now. What will be the effect on the magnitude of the Hall voltage and the direction of the Hall voltage if we keep the current left to right and the field bottom to top, like the diagram, but this time we change the material to an N-type semiconductor? And what will be the effect on the magnitude of the Hall voltage and the direction of the Hall voltage if we keep the current left to right and the field bottom to top, like the diagram, but this time change the material to a P-type semiconductor? I'm about to give the answers, so hit pause now. Okay, so the answers are same magnitude, reverse direction, same magnitude, reverse direction, increased magnitude, same direction, and increased magnitude, same direction. If you got any wrong, stop and try to think why the answer is what it is. I'll continue with an explanation. The first two are simple enough. Reversing the current reverses the direction of the electrons, so the direction of the force reverses. The left-hand rule works for this. Likewise, reversing the field changes how the left hand is orientated, so the force reverses. In both of these, the magnitudes of B, I, N, T and Q are all the same, so the magnitude of the Hall voltage is unchanged. The third one might have caught you out. In a semiconductor, the number density of charge carriers is much lower than in a metal, as in at least 1,000,000 times lower. Since N is on the bottom of the equation, this means that semiconductors produce much larger Hall voltages than metals, so Hall probes are always made from semiconductors. But what about the P-type? It seems intuitive to think that change to a positive charge carrier will reverse the direction of the Hall voltage, but it doesn't. N-type and P-type behave in the same way, and this is why. Firstly, remember that current is going the same way in both cases. Conventional current is going left to right. So, for the N-type, that means the charge carriers move right to left. For the P-type, the charge carriers move left to right. Relative to their motion, they will experience forces in opposite directions. Relative to their motion. In effect, switching to P-type reversed the motion and reversed the force. Two reverses and we get back to where we started. Now at this point, a clarification on the left-hand rule might be useful. We like to summarize the second finger as being the direction of the conventional current. Now this is not quite correct. The second finger shows the direction opposite to the direction of the charge carrier flow. When the charge carrier is an electron, when it is negatively charged, then the second finger happens to match conventional current. When the charge carrier is positively charged, we need to swap to our right hands, and we must still point opposite to the direction of flow. In this diagram, conventional current is left to right, so positive holes flow left to right, so the second finger points opposite to this, right to left. My right thumb is pointing outwards. Back to the N-type, conventional current is left to right, so electrons flow right to left. So using my left hand, the second finger points opposite to this, left to right. My left thumb is pointing outwards. That's all terribly confusing, and perhaps the left-hand rule should be abandoned completely. But it is still very useful if it's used correctly. We've just found that you need to get your head around some pretty complicated physics in order to use it correctly.